An hour. Okay, so welcome again, and so this is the second part of the talk. I would like first to remind you what we did before lunch. So I talked about three electrostatic lengths. The first was the Bjorn length. Remember, it's about 7 angstrom, and room temperature water, it's 7 angstrom, and you don't have control. It's a number. The biohacker length, I talked about it. It's a screening length. It screens the electrostatic interaction. You need salt to have it. And the ranges is between few angstrom, fraction of a nanometer to hundreds of nanometers. And the third one, the Gouy-Chapman length, came when we talked about a charged surface. And the length is related to the surface charge density, and it's also in the range of nanometers, the range, if you put your numbers. And you see that the Bjorn length enter here and here very conveniently. We also talked about the Poisson-Boltzmann equation. So for the symmetric charge, it's this symmetric cinch, nonlinear. For the linearization, you get this exponential decaying function you can see from here. And when you don't have salt, and I showed you the profile, this equation with the boundary condition give you a very nonlinear equation. You see the second derivative goes as e to the minus psi, and you get this diffusive double layer notion. If you add some salt, then this diffusive double layer will be exponentially decayed. Okay, so we did, I changed a little bit. I will not have time to do everything I wanted, so I sort of will skip some of the parts, but I just would like again to remind you, we did already the no added salt, so only counter ion for one charged surface, and the notion of diffusive layer was very natural. You saw this algebraic decaying profile, that this is one of the reasons why they call it diffusive. And when we add salt, there is also an analytical solution. We didn't do it. I'll do it very quickly. And I will not do it, but I will just show you in principle how you can do also the two charged surfaces. So this is now one flat surface with added salt. So I don't solve this e to the minus psi, but it's a cinch. You remember, this is a full Poisson-Boltzmann equation. I have a charged surface with a fixed amount of charge, sigma, and then I connect this system to a salt reservoir of concentration n0, and I need to solve this equation with the two boundary conditions. One is the boundary condition here, the other one at infinity, where the amount of salt is just a constant, the bulk reservoir, and the electric field is going to 0. So this is a solution. I'm not showing you how, but it's actually, when I give a course, I ask the student to solve this. It's not so complex. You can do the second integration in this case also, the first always. And you see it's a little bit more complex. It's not an exponential decay. It's not an algebraic decay. It's in interpolation between the two. You can show that when you don't have salt, this goes to the Gouy-Chapman solution. And when you have a lot of salt and you can linearize, it will go to a simple exponential decay with the lambda d. But in general, it's a trade-off between lambda d and the Gouy-Chapman length. So you see this gamma here depend on solving this quadratic equation. So this gamma depend on the ratio between the Gouy-Chapman length and the Debye length. Depending if this ratio is large or big, you can get the two limits that we talked before. The linearized case and the Gouy-Chapman case with no salt. So this is the general profile, and of course when you know psi, you know also the two profile of the ion density. You see one ion density goes like this, the n plus, it's accumulating close to the surface, but it goes all the way to infinity. The other one is a depletion, and of course when you are far away from the surface, both of them go to the bulk density, as they should. The surface cannot have influence on the bulk. The surface is two-dimensional, and far away, you don't feel the surface. This is a general statement. And for the electric potential, of course, you also have a solution. I don't show it, but basically, this is the boundary condition translated into psi at the surface, the point here. And then once you know this, you know the psi. I mean, I showed it before. Yeah, this is a solution, and this gamma is coming from here. So you basically, everything is analytic up to solving the quadratic equation, and you know everything. Okay, so it's a bit fast, but the details are not important right now, and just the principle. So basically, you can solve the no added salt, the counter-ion analytically. I did it. You can add the salt and solve it. I didn't do it in detail, but you can do it yourself, also analytic. And the other problem that I don't have time so much to I will just show you schematically, is when you have two surfaces, identical charged surfaces, and then without salt, only counter-ion in between, or with salt, what can you do? So when you don't have salt, again, this can be done analytically. There is an analytic solution. And when you have added salt with two identical surfaces, then the first integral can always be done, and the second integral cannot be done because it's an elliptical integral, and you know elliptical integral, this is like one of the special functions. You cannot express it in terms of simple exponential and trigonometric function, but of course you can know everything about the elliptical integral as well. So, and the other case that I'm also not going to discuss directly is the two asymmetric surfaces, which mean you have sigma 1 and sigma 2, and they are not the same. And again, you can think about a system where you just put counter-ion to balance the sigma 1 and sigma 2, or you also added salt and everything is neutral. And most of this cannot be done analytically, but there are some analytic solutions that can be done. So this is, for example, the schematic of a two-symmetric system. You see sigma, I just arbitrarily choose the surface charge to be negative. So sigma is less than 0 on this, and on this there is another length, the natural length, which is the distance between the two surfaces. So I take the distance to be d, you see. So the symmetric plane is a mid-plane. I call it m for mid. So psi m is the potential on this mid-plane. And then you can think about a system where you have only counter-ion, or in this case you have salt connected to some reservoir of salt, and the sigma, in this case I've chosen it to be the same because it's a symmetric system with salt or without salt, only with counter-ion, and these are the two systems. Of course, that what is important in this system is to calculate the free energy. The free energy is the electrostatic free energy, so you have to take into account the electrostatic energy of all charges interacting, the surface with the surface with the ions with the ions, the mobile one, everything together. This is the electrostatic interaction. And then you have entropy. Entropy is of the counter-ion. So you can calculate the free energy. If you know the free energy, you can calculate the force between the plates. And as you remember in the beginning, I was talking about force balance apparatus. There is such a machine where you basically take two mica surfaces, and you can calculate, you can measure the forces for mica is extremely flat surface, and down to a fraction of a nanometer, you can measure forces between those two plates of the range of piconewton to nanonewton. And in terms of the expression, the osmotic pressure is just the variation of this free energy with respect to the distance. So you look at variation where you change a little bit the distance. This d goes to d plus delta d. And you can show very generally that this is, it looks like only entropic term, but it's the entropic term of the mid-plane density minus the density of the reservoir, sum over all ions in the solution. And because this is mean field, just a second, you can show that this obeys the Boltzmann weight factor. You can show that this is always repulsive. So the interaction between two identical surfaces for Poisson-Boltzmann, which is a mean field theory, is always repulsive, which means that it's always, the entropy is always winning over any type of attraction. This is not true in general. It's true only for mean field. Yes?
So basically, you are solving this linearized Poisson-Boltzmann equation.
No, this is not. This is a general statement.
Integrate out the electric potential, and then you.
This is, I do a real variation of the free energy. The free energy is giving, I don't have time to do it, but the free energy is giving in terms of an integral. It's a functional of the density profile. Yeah. And the fact that it looks so simple is a bit misleading, but it is a result because you see because this is symmetric, so the field here, you see it's zero. Because, you know, if you go to the left, you go to the right, is the same. So the variation of psi, a little bit to the left.
What I mean is when you write down the electrostatic energy, you write in terms of the ion concentration and the electric field potential, right? And the D is a parameter. And you need to integrate out this ion concentration and electric potential. Then you found a free energy functional distance.
That's right. I don't need to find the, in order to, you know, this is related to the contact theorem, which is generally true. In order to do that, I don't need to, I need just to say that I am satisfying the variational principle. So the profile will satisfy the variational principle of the free energy. I don't need to find it in order to find this expression. You see, I mean, this is misleadingly simple, but I don't know what is the n of m. I need to calculate it. Okay. And this depends on the potential and so on.
So to calculate this in m, I need to solve it.
Exactly. But I can say general statement, for example, I can show that this is always repulsive. Okay. Although, you know, you have two types of ions, but altogether it's repulsive. Okay. So there was already asked the question, but anyone else? I jumped over some stuff because I want to show you the Manning condensation. I think I have an original way of showing it that usually you will not find it in any book. It's nothing new, but it's just an original way of presenting the Manning. Okay, so I want to go into the Manning condensation, and basically, remember up to now we did one planar surface and two planar surfaces, which I didn't do in detail, but I just showed you. And now I want to go to curve geometries. So the simplest curve geometry is a cylinder, and then the sphere. And I will talk about both. So this is very relevant to polyelectrolytes and to DNA. Of course, you know, a charged polymer also has flexibility, and the flexibility is determined by the persistent length. The persistent length is telling you what is the length for which, if I look on the direction of the polymer, there is no big deviation in the deflection of the polymer. So usually for DNA, if it's a double helix DNA, it's very stiff, and this length will be like 500 angstrom. For polystyrene or single-stranded DNA, very flexible, the persistent length will be few angstrom. So here I'm going to talk about cylinders, and think of the cylinders as pieces of the DNA which are below the persistent length. Of course, this is not a full theory. It count correctly the electrostatics and the entropy of the counter ion. If you have flexible polyelectrolyte, the problem is much more complex. So this theory has a very nice history. It started about in the beginning of 1950s. One big name that is associated with this theory is Aaron Kachalsky-Katzir. He was an Israeli biophysicist, and he and his group at the Weizmann Institute many, many years ago, before I was born even, 80 years ago almost, they addressed this problem, and then Manning addressed this problem together with Osawa in the late 60s. Okay, so think of the motivation is a dilute polyelectrolyte solution where, as I told you, I consider the polyelectrolyte as little cylinders like that, charged cylinders, and I don't take into account the flexibility of the cylinder because this is by itself another issue and it's not addressing this problem. Not that it's not important, but it's just not for this problem that I'm under. So there is something that is called the cell model. The cell model, very simple, is you take a cylinder. I will not take the finite size of the cylinder. I will assume that the cylinder is infinite, again, approximation. And because each of the cylinder has somehow another type of area, you can say a cylinder that is sort of limiting the counter ion that is around it because you have a dilute solution of polyelectrolyte, I will say that I have an inner cylinder and an outer cylinder with the salt that is associated with this cylinder. Now, because you have all those different cylinders, the most natural boundary condition, again, this is not exact, would be to take the boundary condition on the cylinder to the inner one to be charged. So there is some charge density on the inner cylinder, and on the outer cylinder, I will take it to have zero electric field. Because, this is the boundary between the different cylinders. Again, this is very natural, but of course, it's not exact. So this is the inner cylinder charge. So you see the sigma is like before. This is the density on the surface of the cylinder, yeah? If this is the cylinder, infinite cylinder, so I have a charge density here, but it's much more natural to speak about a line density of charge. The line density of charge is how much charge I have per unit length of the cylinder. So you see this is a simple 2 pi a is a perimeter, and then sigma over E, I do over E so to get number density. So it's a charge density in units of E. Line charge density in units of E. So charges per unit length. So this sigma is charge per unit area divided by E. So this is 1 over area times A. So this will give me 1 over length. So the charge line density is measured in units of 1 over length. And as I told you before, the outer cylinder is a zero field because this is the cylindrical geometry. The field is just the normal derivative, so it's psi which depend on this direction. So the derivative of this at the perimeter R, remember that R is a cell size, contain all the counter ion that are within one of the cylinders, and I forget about all the rest. This is my system. So the field should be 0, which means that the derivative in the normal direction of psi should be 0. And, sorry, somebody has a question? Yeah.
The ratio between A and R is like a volume fraction of the cylinder, or you will not necessarily? How do you take R?
How do I take R?
A is a real
Yes, that's right. So R, if I think about the physical system, so R is the specific volume per. Yeah. So I have a density of chains.
It's a
density of the chain itself. Yes. So I associate this, and let's say if I dilute it, this R will increase. If I condense it, R will decrease. Of course, this is a parameter. Yeah. Okay, thank you. That's a good point. Okay, so look at this equation. It looks a little bit misleading simple. So what is the difference with the planar geometry? In the planar geometry, of course, we didn't have this term, yeah, because the Laplacian in one dimension, the Laplacian is just the second derivative, and that's all. In cylindrical geometry, although you have the Laplacian, although psi depends only on the distance that is normal to the surface of the cylinder, not on the angle, yeah, and not on z, not on because it's translational invariant, you do have this other term. So you have 1 over r d psi dr. So the difference is that this equation it's still linear. You know, if I do on the Debye-Hackel, so it was a sinh here or a e to the psi, and now this is linear. But this term means that it's always like this, yes? If you look on Helmholtz equation in 2 dimensions with cylindrical symmetry, you will have this type of term, which means that the coefficient of the linear term depend on r, which means that it's not a simple, the eigenfunction will not be simple exponential, but will be, you know, usually Bessel function, something like that. But in principle, we know how to solve this. This is a linear, and the linear one is not the most interesting case, but it's just for you to see. So it's very easy. I know the boundary condition. You saw the boundary condition on the cylinder, the line density is given, and also the boundary condition on the outer cylinder is given because the derivative there is 0. And if I now look, I don't want to show you the full expression, although it can be done analytically. You probably did it for various courses. But if you look on what I call infinite dilution, which means that this R is much bigger than A, when, you know, the distance between this cylinder become as large as you want, then basically the psi is a Bessel function. K0 is one of the Bessel function. It's not the first kind. I don't remember it the second time. But it's one of the Bessel function, and those Bessel function, K0 and K1, are the first. And they all decay exponentially when the argument is big. So basically, you see, we recovered e to the minus r over lambda d. But, and this is related to your question, in this cylindrical geometry, there is also 1 over square root of r, and this depends on the dimensionality. For sphere, in 3D, it will be 1 over r, but for cylinder, is 1 over square root of r. So, you see, so what this tells you is that most of the counter ions are within this yellow cylinder, which is as the size of lambda d. So most of the counter ions are concentrated close to the cylinder, and then you decay to 0. But this is not so nice. I mean, it's nice, of course, but this is not the nice case of the condensation that I have to show you separately. So for the condensation, there are several important conditions that people usually forget. And what happens when they forget is they take this Manning condensation outside the range of validity of. So it's very important that you remember when I can make the statement about the Manning condensation. The Manning condensation, there are 2 important statements. One is that I don't have salt. If I have salt, it's like I'm rounding a critical phenomena transition. Salt will round everything and will not cause a transition, like what you will see. So you see, on the right-hand side, I have only e to the minus psi. I don't have the sinh, because I don't have salt. How much counter ion I have? I have counter ion in such a way that this system is neutral. So this is one condition. The history of this problem, so these are the 2 important dates. One date is that Aaron Katsir-Kachalski was a very important scientist in Israel in the Weizmann Institute. Lifson was his student. Foss was an American chemical physicist from Yale. And all three together, although I think the work was of the student, as always, in 51, they found an exact solution. So you see, the equation is not simple, but for cylinder, there is an exact analytical solution. For sphere, for example, there is none. But for cylinder, there is one. And they found an exact analytical solution for a finite R. So R over A is finite. And they found the solution. What happened, you see, like almost 15 or 20 years later, 69 and Osawa in Japan in 71, they found, Manning did it in a very hand-waving way, and Osawa did it, he has this whole book, and he explained it. And also, there is this nice review of Zim and Lebre, and also in my review, what I'm showing here, I did it already there. So what they showed is that there is a phenomena that is very special, where the counter ion come and condense from infinity to the cylinder. And this is something I would like to explain you. And I will explain you in a way that is a bit different than you find in the literature. So, also in the original work of Foss, Kachalski, Lifson, they did the mapping that I'm showing here. They said, let's do the mapping, and this is very, very common to two-dimensional system. You have all this type of mapping of sphere and cylinders and circle into plane and so on, like conformal mapping. So what they said is, instead of looking at R, let's look on log of R over A, and let's call it Z. And you see, first of all, that the Bjorn length enter into all this consideration. And this is one of the reasons why I explain you the Bjorn length. It's entered very naturally on this consideration. So when you take this mapping and you look on the boundary condition on the inner cylinder, you remember here the boundary was that you had rho. Rho was related to the charge density, the surface charge density. Remember, it was A times sigma over E. So you get that from the inner boundary, when you take this one map into a planar surface, and the charge on the planar surface is exactly what I write here. 1 over LB, 1 minus rho times LB. So the first thing you see immediately is that 1 minus rho LB can be either positive or negative, depending if rho LB is bigger or smaller than 1. And this is starting to be interesting, because you see, if this condition goes through 0, you get either positive or negative surface charge here. Now, this one, remember, was psi, which was the derivative of psi, which is 0. And when the derivative of psi is 0, it maps into a boundary condition that is always negative. The amount of surface charge here will be minus 1 over LB. So it's like, you see, it's like this one goes into minus 1, but without this. So why do I show it? Because the mapping get rid, you see, the mapping get rid of this ugly term. Because in the planar geometry, I know to solve the problem. It's just a planar one, which means that the second derivative of psi is equal to e to the minus psi. And I know to solve it. I didn't show you, but I know to solve it also when the charges are not the same on the two boundaries, and also when one of the boundaries is negative and the other one is positive. So it's possible to do. So you see Z now here is the distance here was this mapping of log of R over A. So between the two boundaries, you have log of capital R over A. And in between, I can solve the planar geometry. So this is the trick. The trick was used also by Kachalski, but okay, you will see what I mean, but this representation in terms of geometry was not done. It was just writing, let's do the transformation from psi to, from little r to log R over A, and then to transform the potential psi into something else and to solve it. Okay, so it's very important that you tell me if you understand. It's a mapping between a curved concentric two-cylinder into a planar case where the two surfaces are not equally charged. And one can be positive or negative, and the other is always negative. And this problem, the planar one, I know to do. So it's always in physics like this. Yes, we map to something that we know, we solve it there, and then we take it back to something we don't know.
Planar interface infinitely large?
Infinite.
Okay. Even the, how can I say, this cylinder is finite.
Yeah, look, because if you look on the log, So when z is equal to a, and r is equal to a, log of 1 is 0. So this is z equals 0. And when r is equal to capital R, then log of r over a goes into z, not into r, but into some constant z. Yeah, it's like we always play these tricks, yes? When we solve two-dimensional electrostatic problem, we can always do this type of mapping. Yeah, so it's infinite. Infinite and constant charge. Anyone else want? I mean, this is very important. If you understand this, you will understand the rest.
So that list will contain the solve inside or only counter?
Only counter ion. I mean,
it works only for.
I can do the mapping also, but I cannot solve it.
You can do it for also secret for.
Yeah, but the mapping takes care of this, but then with the cinch, I will not be able to solve it. And also, if I try to do it for spheres, for sphere is very, it's, instead of 1 is 2. Doesn't work. So it's like an accident that I don't understand really why, but for sphere, to do the sphere with salt, extremely complex. I mean, mathematicians really spend a lot of time on that. Okay, so let me pictorially show you how it works. So now we go, I want to explain you the condensation of counter ion, and I don't think about, I will come back to the cylinder later, but now I talk about the equivalent two surfaces. So case number 1, rho is less than rho star. What is rho star? Rho star is 1 over LB. So for people who know the Manning condensation, you already recognize that this is indeed the concentration which is equal to 1 over LB, which is for water, monovalent ion, it's 7 angstrom. So something happened when you have charges more than 1 charge per 7 angstrom, and you remember DNA was 1 charge per 1.7 angstrom, so it's much more. So small rho, this is the first case. Small rho would mean that one surface is positively charged because 1 minus rho LB is bigger than 0. This is exactly this criteria. The other one is always sigma 2 LB is always minus 1. Remember, because it was minus 1 over LB, the surface charge. And these are surface charge densities, the sigma. Okay, so one is negative, one is positive. The inter-surface distance d is just log of r over a. And now let's take the system of two surfaces and gradually make the distance as large as we want. Take this r to infinity. Now you see, this is only counter ions. So the counter ions will be repelled from this surface, and they will be attracted to this surface. So when you make the distance, of course, when it's finite, there will be a profile. But now when I think about a system where I take the lower one to infinity, all the counter ion will run away with it. So this is the case where if I take this, the distance to infinity, meaning that this goes as down as I want, all the counter ion will follow this one, and because they are repelled from the upper surface, so basically it's what is called they run away to infinity, and the solution is just no counter ion inside. So the ions are repelled from the top surface. Entropy always win because you have, as you make it as large as you want, you know, at infinity you have a lot of entropy. You don't confine any charges in between. And this is no condensation of the top surface. Remember that the top surface is, when I map it back, this is the inner cylinder. And this is this outer cylinder of R. This is the inner cylinder. Should I repeat that? Maybe. See, this one is this one. Yeah? And now I talk about the case where this is negative, and this is also, I'm sorry, this is 1 minus rho is less than 0, so it's positive, and the other one is negative, so all the counter ion run to infinity. How about the second case? The second case is when I'm charging more and more the inner cylinder, which means that rho is becoming bigger, which means that at some point I will cross 1 minus rho Lb equals 0, so all this is negative. So I have negative here and negative here, and in between I have positive counter ion. Now, I'm not showing you, but you know, this, I can do this for any sigma 1, sigma 2. The ions are attracted to the top surface, and not all of them run away to infinity. So some of them do, but some of them don't. So some of the counter ions are left behind. And this is exactly the Manning-Osawa condensation, because when I take apart the two surfaces, it means that I'm in the infinite dilution. I have only one cylinder. The cell size is go to infinity. And some of the counter ions stay close to the inner cylinder. You see why. I mean, for the planar case, it's very easy because one is positive, one is negative. For the cylinder, it's much more complex to understand why this happened for rho equal 1 over Lb. But in this type of explanation, it's quite clear. Let's now go back to the cylinder. So remember again, I have no salt. I have a charged cylinder, rho, per unit length, and I have counter ion. So I do again the two cases. This is a case where the inner cylinder charge is small, smaller than this critical value that is 1 over Lb. And when I have my outer cylinder that goes to infinity, all the ions will go with it. Why? Because they will gain entropy. I will show it also in a different way. So the only solution here, when rho is less than rho star, is that no counter ion exists. All of them run away to infinity because basically you see, if you have a cylinder, if I look far away from the cylinder, there is much more area, yeah? Because look, if in the cylinder it's like this, and yes, and I look on rays like this, I have much more area. The entropy always wins when rho is less than rho star. Now, if rho is bigger than rho star, meaning that I'm charging more, some of the counter ion will still be attracted. They will not sit on the cylinder, but there will be a profile that is left behind. Not all of them, but some of them stay behind. How much of them stay behind? They stay behind so that if I integrate their profile together with the line density of the cylinder, the effective line density always stay on this value of 1 over LB. And this value 1 over LB for monovalent salt, room temperature water, is 1 charge per 7 angstrom. So DNA, we talked about it again. It's about 1 charge per 1.7 angstrom because it's a double helix. And this means that if I put 1 DNA in an infinite diluted solution with salt, effectively the counterion will come and will make the charge of this DNA to be about 1 charge per 7 angstrom, so not 1 charge per 1.7. So this is why it is called the Manning condensation, Manning-Osawa, because the charges come, they don't sit on the cylinder. Again, another mistake that many people do, they think that really there is a profile, and I can show you. This is a profile, you see? So you can calculate this profile both for finite cylinders, outer cylinder, and for the infinite dilution. This is the profile for the infinite dilution. It is a complex calculation, but it was done. And you see there is a whole profile. But this whole profile is, you see again, the condition that when LB rho minus 1 is 0, something special happens. And effectively, if I integrate this profile, it's exactly will balance the charge on the cylinder rho in such a way that the combination of the two is always rho effective. And this is the threshold of the Manning-Osawa condensation. Okay, so this is
Is there
yes.
any typical length scale in this expression? Only LB? No typical length scale in this profile? Like Gui-Chapman or nothing?
1 over rho is the length scale, yeah?
Okay.
Yeah, so it's always 1 over rho compared to LB.
Okay.
So rho plays the role of the Gui-Chapman length. There is no Debye because it's only counterion. There is no salt. If you have salt, you just have the Debye screening will round this transition. So this is sort of important. You see the fact that you can say, okay, I have many people, when you look, especially in biophysics, when they do consideration, let's say, of DNA, they say, yes, the charge of the DNA is always 1 charge per 7 angstrom because they're rho effective. It's not exactly like this because the DNA has a charge and then there is a profile. It's true that the profile is very much around the cylinder, but there is a profile. So to say that rho effective is 1 over LB is already by itself an idealization. So there is a cloud. And when you have a finite road, when you have a mixture of several counterion, when you have multivalent ion, and especially when you have salt, this consideration has to be taken with a grain of salt. You can show how the limit is, but this is an idealization for infinite dilution and no salt. And then you get really a transition, because as you remember, when rho is less than rho b, all the counterion run to infinity. When rho is equal to rho star, 1 over LB, they come and they neutralize the surface. So in the beginning, it will be 0, and then it will grow from 0 so that the rho effective will be just 1 over LB. So I want now to put the perspective, and this also is something that usually people don't do so much. So think now about, we talked before about the planar case, and the cylinder case is special, and there is also the sphere. So one surface with counterion, there is always condensation, because I've shown you that irrespective of how much will be the surface charge density, there is always a profile. A profile means that there is always condensation, And the reason is that, if I look here on this little box that I'm drawing, you see that different surfaces on this box have the same area, which means that the entropy of ions, if they are close or far, will be the same. Now, think about the sphere. The sphere is d equal 3. So without any calculation, I can show that in this restricted limit of no salt, just counter ion, entropy always wins over electrostatic interaction. Why? Because you see, if I look here on a little piece on the sphere where I have some charges, and I look now on concentric sphere, of course, I have two directions where this area grows. And the fact that I have two directions means that the entropy will grow much more than the attractive of the electrostatic interaction. So the sphere is an example, d equal 3. Charges always run away to infinity. Of course, if you add salt, or if you have a finite container, an external sphere, there will be a profile that cannot run away to infinity. But in this mathematical abstract limit of infinite dilution, no salt, all the counter ion will run to infinity. There is no other solution. And this is the cylinder. You see, it's in between. And this is why it's interesting. It's in between because both the entropy and the electrostatic interaction in 2 dimensions, you know that it's logarithmic. Entropy is always logarithmic. And the electrostatic interaction, if you look on interaction, the potential close to a wire, it's also always logarithmic. So the two terms are logarithmic, and it depends on the coefficient between these two terms because they compete. And if rho is less than this rho star, all counter ion run to infinity. If rho is above this rho star, some of them come back in order to stabilize, neutralize some of the surface charges. So this is why this case is so interesting, because it's in between. So always condensation, T equal 1. Critical condensation for the cylinder, the Manning-Gauss and always no condensation in D equal 3. Okay. Yes. Oh, the first question. Yeah. From a student.
You have a protein condensed.
But say it again, please.
A sphere-like protein condensate, and we put this sphere-like protein into a pure water. And so does this mean the proton will just spread out and leave the ions just as the sphere of the condensate?
Okay, so I think the right way to think about it is you have, protein or whatever, you have some colloid with some charge, and then I enclose this sphere with another sphere, and the system is neutral. So the number of mobile ions exactly equal to the number of charges on the sphere, okay? And so it's just the Duncan thought experiment. And then I take the outer, I can do it because, it's abstract. So I take the outer sphere slowly to infinity. This means that all these counter ion will go with will go to infinity with why? Because the entropy, is winning. If you have salt, no. If you have salt, it doesn't work. If you have this, you have other protein close by, then you cannot think about this infinite dilution. So this is just a mathematical limit, but it's an important limit. Yeah. Any other questions?
Just a quick
Yes.
question. So in the previous slide,
Mm-hmm.
so for D equal 1 is the Gui-Chapman case.
That's right. And you don't think about it like this, but I would say for the Gui-Chapman, always condensation.
I understand. But then you have this Gui-Chapman length in that case.
Mm-hmm.
And my question was, for d equal 2, is the corresponding length scale, like Gui-Chapman length in this d equal 2 case? I mean, I didn't really, in the previous, this looks like just 1 over r squared, almost.
Yeah, but that's right. But you know, you have this log here, yeah.
But this,
You see, I mean, this rho here plays the role of the Gui-Chapman length. Remember, because rho is the line density. The Gui-Chapman length is 1 over sigma.
so rho, 1 over rho.
1 over rho is roughly plays the role of the Gui-Chapman length.
Okay, and rho is determined by the surface.
Yeah, I mean, it's better to do the mapping and to solve. I mean, for the mapping, of course, you have the Gui-Chapman length, but because you have two surfaces, you have Gui-Chapman on one surface and Gui-Chapman on the other, because each one depends on the surface charge, the effective surface charge density on the planes.
But in the Gui-Chapman case, you have a r squared plus Gui-Chapman length.
It was 1 over r plus.
Yeah, but this is just a multiple. So I'm not sure if this really.
Look, if you, of course, I can take after doing this, I can, and this is possible. I can do now the limit of A that become as big as I want, so that the curvature of the inner cylinder, after taking the limit of the external r to infinity, I now will take the limit. It's perfectly okay, but it's not. I agree with you. It's hard to see from here, but it can be done. It was done, and you are mapping back into the Gui-Chapman, and but yeah. Yeah.
Okay, good.
You can map, and also you can do it with salt and take the limit of it. Salt goes to 0. Yeah, you are right. It's not so simple. Some of this limit, you have to go into the complex plane because like the sinh become a sine and so on. But it is possible to do it. Any other questions? Okay, the last 5 minutes, I want just briefly to talk about the sphere. So you remember I talked about one sphere with no salt, and I said all the counterion run to infinity. Usually, we don't have one sphere, and we do have salt, like in a colloidal suspension. And the question is, how can you stabilize with electrostatic this colloidal suspension? And I will do it very briefly. So the first thing is to look at with salt, with lots of salt, and then I'm linearizing the equation. If you look on the linearized equation for cylinder, we never will get the Manning-Osawa condensation, because the Manning-Osawa condensation you get only when you have e to the minus psi here, and the linearization of the sinh when you have salt give you this equation. Now you see the only difference between the cylinder and the sphere is for the sphere you have two. In general, if you look at any d dimension and you look on hyperspherical geometry, the coefficient, if you don't have any angle dependence, the coefficient is always dimensionality minus 1. So in 3 dimension, you see it's d minus 1 is 2. In 2 dimensions, it's 2 minus 1 is 1. And it's amazing, but this is how it is with nonlinear equation. It's enough that I will change 1 to 2 in the coefficient, and I can go from having an analytical solution to not having an analytical solution. The mapping that I do works, but it will give a very complex equation, so I'm not gaining anything in simplicity. Now, this is one charge sphere, you see, A. This is now a sphere, not a cylinder. The charge on this sphere is Q times E, let's say negatively charged. And then I have salt. And if I have lots of salt, this is the equation I have to solve. Again, a Helmholtz equation in spherical geometry. And you know that the eigenfunction of such an equation are the spherical Bessel function depending on the boundary conditions. And this is actually was already done by Debye and Haeckel 100 years ago. And you can, for one sphere and in this limit of high salt, you see you have e to the minus lambda over Rd, like we had in the Debye, but now it's divided by R, because again, the power of 1 over R to some power depend on the dimensionality, and in 3 dimensions it's 1 over R. And then also this coefficient here, you see Lb enters here, and this coefficient basically comes from the boundary condition that now is on a sphere. So this is psi. You see, it's decaying exponentially because you have lots of salt, so it's decaying exponentially far away. But it doesn't decay as a pure exponential. It decays as a pure exponential multiplied by an algebraic function of, in this case, 1 over R. Remember, for the cylinder is what? 1 over square root of R. And this is, these are Bessel function, spherical one, which goes into 1 over R. The regular Bessel function goes into 1 over square root of R at the asymptotic limit. Okay, so now come the following thing that was done by Deryagin and Landau and Overbeck and Verwey, the LVO theory. And this is a theory where you look on a colloidal suspension. But let's say I'm looking about interaction between two colloids. They are identical, so let's say both of them have positive charge, and they are separated the distance capital D, and between them there is salt. And the question is, what type of interaction there will be in between them? So the electrostatic interaction, also for sphere, always negative. In order to get a positive electrostatic interaction, you need to go more than Poisson-Boltzmann. This was a big debate, and it was 20 years ago, it was proven exactly that for any shape geometry, but with identical charge, there always will be a repulsive electrostatic interaction within mean field. In order to get something that has an attractive component, you need to go beyond mean field. We will not do that, but you saw in experiment of the spooling of DNA with multivalent ion that this is indeed the case. So there is always a repulsive interaction. In the limit that this D is bigger than lambda D, the repulsive interaction between two objects to leading power will go as exponential, the Debye length. So it will go exponentially with the Debye length, and this is repulsive. The other thing that we didn't account for is van der Waals. So van der Waals interaction always exists between any two bodies, and this has to do with the fact that any two dielectric material, even when you have a different media in between, you will have induced dipoles, and those induced dipoles, because they can fluctuate, they attract each other. For this type of geometry, again in the limit that this is in some range comparable to the size of this sphere, it will go as minus 1 over d squared. This is just hand waving. It can be calculated in more detail, and it's not exactly 1 over d squared, but it's when the distance is short enough, this have a strong attractive component. Now, I take electrostatic repulsion with van der Waals attraction. You see one goes as e to the minus d, and the other goes as minus 1 over d squared. I plot it together, and what do I get? You see, when d is very small, I get that the electrostatic is winning, and there is a strong repulsion. When both of them are small, the distance is big, I get that this interaction between the two is going to 0. But what is interesting is the fact that beside this minima here, which is a minima that basically correspond to sticking of the particle together because of van der Waals, there is a secondary minima here. And this secondary minima is basically the reason of stabilization of colloidal suspension. This minima here that is due to van der Waals is basically sticking. The fact that you have here this very high barrier has to do with the fact that, that there is a finite size of the particle, a steric repulsion. But this minima is basically the sticking minima, and you don't want to enter here, because this will mean that everything sticks together. But you see there is a barrier here, it's some fraction of kT, and there is a minima here at some d star, which has to do with the competition between these two terms. And this d star basically is what is giving you the colloidal stabilization, because it says that at some distance the colloids will have a balance between the repulsive and attractive interaction. And this, I mean, it's a hand-waving way, but this is basically at the source of the famous DLVO theory. Of course, you don't have to, you can do the electrostatic repulsion not only, let's say, in the, for the linear case, you can do the full electrostatic of this, maybe have to do it numerically. And van der Waals also, we know how to do it, and there is, the expression is more complex, but it doesn't change, it changes quantitatively, but not qualitatively, this argument. Okay, so I think I will stop here. So the take-home message is that we do have charges in any aqueous solution, including biological system, many liquid solution in industry, in chemical application, and they do play an important role. I just talked about very simplified cases, but you know, rigid and very well-defined geometries. In general, you know, you have a protein have a very, you know, convoluted shape with charge that is not completely uniform, but you know, the charges are on some isotropic charges, and that you have to take into account. Usually, in order to do it, you need to do something numeric. You have to solve a very complex boundary condition of the Poisson-Boltzmann if you stay within Poisson-Boltzmann. There are other geometries, like I discussed, the cylinder, where you get the DLVO, and where you get the Manning-Osawa condensation, the DLVO that you get for salt together with colloidal charged particles. You can now also think about flexible objects, like a flexible chain or a flexible membrane, and then also calculate what is the effect of the charges on the flexibility. It's usually not quite a difficult problem. For example, for polyelectrolyte, there is no very well, you know, established full theory of polyelectrolyte, where you take into account, besides the polymer flexibility, you take into account also the electrostatic degrees of freedom. There are many approximations, but there is no full theory like there is for a flexible polymer chain, that we know that it's a Gaussian distribution, and we can do many things about that. Okay, what I didn't cover, it's impossible, even, you know, what I wanted to cover, I couldn't in 2 hours. So I didn't cover things that are more modern, correlation and fluctuation that go beyond Poisson-Boltzmann. And for example, in order to explain the condensation of DNA in presence of multivalent ions, the fact that DNA can fold on itself, so although the DNA is so strongly charged, there is an effective attraction, and it folds on itself, like I showed it in the spool. Due to ionic bridges, it goes beyond this simple theory. Surface tension of electrolyte, we mentioned it a little bit with Xinpeng, but there is a famous theory of Onsager and Samaras from the 30s, again, was very much ramified in recent years, where basically the surface tension of seawater is higher than the surface tension of sweet water, pure water, due to the effect of electrostatics. I didn't discuss that. Ionic specific effect, which has to do with the size of the ion, the hydration shell of water molecule around. This goes beyond the fact that we took always the dielectric constant of water to be epsilon equal 80, and we didn't think about any order parameter of the dipolar of the water molecule around ions. Another interesting theory that again was studied over the years is conductivity of electrolyte solution. When you have a concentrated electrolyte solution, there are interesting non-mean field deviation. Also was studied recently. And the electric decrement of ionic solution, meaning that the epsilon of water together with some molarity of salt will not be 80, but it will be less than 80 because the ion basically immobilize some of the dipolar water molecule and the response will be less. And of course, there is much more. So I think this is the end of my lecture. Thank you for the attention. If you have any further question, please ask.
Thank you very much. So it was a very nice pedagogical lecture, and we were a bit behind the schedule, but I can accept maybe 2 or 3 questions. At least one.
So the money compensation is in different dimension. The behavior is different. It's purely because of the dimension, different level of dimension.
In the simplified model with no salt, it's purely a question of dimension, and you can see it in the following way. If you look on the entropy as function of the distance from the cylinder, entropy is always logarithmic. Yeah? If you look on the electrostatic interaction, one charge close to an infinite, it's also logarithmic, yeah, in 2D. It's not 1 over r, yeah, it's in 2D. And then you see log of r and log of r, and then it depends on the coefficient. And the coefficient depends on how strong is the charge.
Yeah.
So this is a hand waving way. For the sphere, the entropy is again logarithmic, but the electrostatic is 1 over r, and it's cannot win over the log. And for the planar, the electrostatic interaction is much stronger than the log. So this is more or less hand waving. Yeah.
So through this mapping, right, from the cylinder to planar, so the charge neutrality is of course okay, right? Even if charge neutrality is
for any finite system,
it's always okay. Right?
It's okay, but you are right because when the charges are run to infinity,
Yeah.
you are left with a charge object with no charges. But you do it in the systematic way. You don't assume that so for any finite system there is charge neutrality, but when you take this artificial or this arbitrary limit that the others charge go to infinity, you will in some cases you will not get a charge neutral system. Yeah. So this is a delicate point. Yeah, it's not so easy point to. And this, I always okay. This is not. I'm just because.